welcome to day 3 of the 12 Days of LiDAR. My name is Alex Billick, and today we're going to be talking about LiDAR classes and classification. So, recall now that we've covered some of the lingo, and also you now understand those basic derivatives that are usually available along with a LiDAR point cloud if it's publicly accessible: a canopy height model, a digital elevation model, and a digital surface model. So, now we're going to dive into being able to extract a little bit more information, and that is some classes that can describe what the lidar is actually telling you. Before we look at some data, I'm going to bring up a resource here. It's from the ASPRS, the American Society for Photogrammetry and Remote Sensing, and they have developed the LAS point cloud standard. We're in version 1.4 now, and we started with 1.1, and there's been a lot of changes throughout those. Some of the changes include how data is organized, the number of standard classes there are, a number of different things. So if you are interested in following this, then I would suggest subscribing to that and checking out the standard. The full standard document is 50 pages, and then they have a 10-page sort of summary of the latest spec for 1.4. Beware that some software packages, if they're older, may not understand LAS 1.4, so they may only work with certain versions. You can convert between them using things like LAS tools, but that is a bit of a challenge, so just be aware of it. Looking at Esri's website for ArcGIS Pro, they do have a good summary table here. It's not comprehensive, but we'll use it as a starting point for the standard ASPRS classifications for LAS. And what's nice is if you collect data and it's properly classified, then this is going to be the standard across the board. So class 2, when you start trading LiDAR data, is going to mean ground. You're going to get to know that. And different software packages anticipate that class 2 means ground. So it's important that you follow that standard. For forestry applications, 3, 4, and 5 are different levels of vegetation. Those are generally driven by just some specified height break that causes that differentiation. You may use some other ancillary data to drive that. Class 9 water is another important one, and we've got a number of others here as well that you can read. This is not a comprehensive list, but it is important to note they've got a few notes here that the LAS classification 1.4, the reason the version matters is they created some new codes that are baked in going forward that may not have been the case going backwards. So class 8 now is a reserved number for model key points, and class 12 is reserved for defining points that reflect overlap between flight lines. That wasn't the case in previous versions, so if you have previous point clouds and you bring them forward, it may appear incorrect, or if you bring a 1.4 backwards, it may not appear the way that you expect. So be aware of that. If you go to the LAS specification, the 1.4 document, go down to page 30 here, you get a bit more of a comprehensive list. The one I wanted to just highlight to you, because I think this is very interesting, is class 22, a temporal exclusion. So you can actually classify things, and I'm going to show you an example of having done that, like cars, for example. So if we look at a parking lot and that a car is a transient object, you can actually have our classification respect that and say that it's in our point cloud, but it's not something that represents what's going on right now, so we're going to get rid of it. It could also be water levels or some other change between them. So that's an important layer, especially when we get into LiDAR change detection. So I'd encourage you to check this out if you're interested, but that's a publicly available document. Jumping into the point cloud. So this is the same point cloud as yesterday now. This is as I downloaded it from Ontario GeoHub. And we see that the color scheme here kind of makes sense. I mean, we've got some errors here, obviously. Not every building in Thunder Bay has a green roof, so there's an error here. But where do you start? Let's say that you are flying drone-based LiDAR, or you get LiDAR and there's no classifications at all. It just says unclassified. It could look something like that. I'm just colorizing it, but that idea, where would you start? Well, the easiest place to start is from the ground. We know that the last returns should represent ground. We can do some filtering on that, but that's generally where you start. So I haven't really seen a data set delivered that was completely unclassified. It's usually ground and everything else isn't classified. And then what you can do from there is maybe use water layer to pull in and identify where the edges of water are. LiDAR doesn't always behave properly on water. You sometimes get really big spikes. You might, have a log floating on the surface that causes the reflection. It might be shallow enough that you get a reflection off the bottom. So LiDAR, especially if it's near infrared, gets absorbed, but green band can see through water. So the type of LiDAR you're flying matters in this case. But usually what we'll do is we'll take a lake layer or a rivers layer, if it's large enough, and use that to kind of cut out what is water, and we get rid of that data, or we store it somewhere else, because it adds a lot of noise. So usually if you see it, it might say that the data has been hydro conditioned, and that means that they have actually made sure that water flows downward, and that it also may mean that they have gone through and cut out all your culverts or all the places where rivers go under a road, for example. So it just depends if that has been part of the acquisition specification or not. So let's look at the classes again here and see what we've got. So we've got some yellow in there. If we turn that off, that's our overlap. So we can see that this on campus here was actually an overlap between two flight lines. And then we've got different levels of vegetation. So let's turn off our high veg, our medium veg, and our low vegetation. And then we'll zoom down here. So we've got a few things that represent noise. Could be some air, whatever it is. So we're going to turn off our noise. And then we see here that this looks like an artificial deck of some kind that's been classified. In this particular viewer, I can't pull that up, but what I can do is draw a quick line over top of it, show the 2D profile, and then see what classification it is. In this case, it is class 17. Looking back here, 17 is a bridge deck. So that makes sense. This particular viewer was created before version 1.4, so it doesn't have visualizations for all of the extended labels that are there. But we see here another bridge deck likely. So we've got some pretty good performance here from the base data that was supplied by the ministry. The problem is that, obviously, our buildings are called high vegetation, and this is pretty common. The intent of this data is forest resource inventory. So they're not going to sit there and spend additional time and money to classify it into buildings for urban forestry use or urban planning use or whatever the case might be. It doesn't make sense. So the data is there, though, and we can start to refine it. Now, how do you go about classifying other things? Well, in this case, what I would use is you could either use something like OpenStreetMap. They have a buildings layer that you could use to help you identify the footprints. But what I've done instead is gone down the classification route. So I've taken some samples and said this is an example of buildings, and then I fed it through a classifier, and we'll take a look at the results. So I'm going to turn off that point cloud, and I'm going to turn on the first one here. And we see that it's pretty good. So buildings now have been pulled out. What I might do in the future, looking at this, is that those things that were bridge decks before have been called building. What I could do is just exclude that class the next time I run it, and then it won't get pulled in. So I might do that just to keep this all clean. But otherwise, it's pretty decent. We've got some error happening here, and that's probably just because we've got a canopy right next to a roof. That's always going to be challenging. Rather than try to adjust the algorithm to catch all of these edge cases, it's sometimes easier just to come in and manually clean that up if it's especially a small area like this. But it's pretty good visualization here. So I'm pretty happy with that. And now we can actually take a look at this. We could turn off our high vegetation and just take a look at the buildings around campus here, for example. Now we see all these cars in the parking lot. Let's take a look and see what class those are called. So again, I'm just taking a profile here, and we see that they are classification 22. Recall that class 22 is that temporal exclusion. So we've actually pulled out all of the cars in the parking lot, and we can say that, yeah, we don't care about those. They're not part of our analysis. If we're going to fly this again, we don't want to follow those. So I'm just going to turn off those. And now if I output some data, I'm not going to have all that noise, which is nice. So if I said I need a digital elevation model and I didn't want that getting confused, now I've cut it out and I could fill in those gaps and then export this data out. So it's a nice way to be able to use this. Again, turn off our overlap and we can explore this data set. Now, how do I know this is an error? What we can do is go one step further actually, and we could actually add color information to it. So what I've done here, exact same thing, but now we're going to change it to RGB. And now we have a colorized point cloud. So now we can see what's going on here. Now this imagery was not flown at the same time as the LiDAR, so there definitely would be some temporal exclusions here that would cause errors. So this is a good example of that, where in the image we see car profiles that may or may not be populated by a vehicle, and then we see ground getting populated by something that isn't there. But if we turn that off, we can get rid of it and at least it's flat and we don't see that. The imagery, well, different story. But this gives you an idea of what's possible and why LiDAR classes are helpful. Looking at the roof here, yeah, it's just a case of the vegetation is right there. And so being able to pull that out with classification, I think I would just probably go in and manually clean that up quickly. Um, because I feel like it probably caused more errors if I tried to fix it algorithmically. But maybe not. I might just grab some samples. Who knows? I'll give it a try. So that's an introduction to LiDAR classification. Highly encourage you to take some samples and give it a try to see how you can develop your own classification scheme and maybe try extracting the building footprints yourself and see what kind of success you have. Thanks for listening.